Hi everyone, I welcome you to the presentation of this lecture on magnetostatics. So magnetostatics basically is the study of magnetic materials and their properties, of course properties of attraction and repulsion and many more. Though in this presentation my focus is not really on the properties themselves, is on the calculations. So I'll focus much on the calculations. So I'm going to introduce parameters. We are going to start with this parameter, which I'm calling the magnetic flux density. So magnetic flux density has B, capital letter B as a symbol, and the units are Weber per meter squared. Okay, this will relate it to another property, which we are calling H, and the name of that one is the magnetic field strength. So the magnetic field strength have units called ampere turns per meter. Then we have another property which we are introducing there, which we are calling the magnetomotive force. So the magnetomotive force is measured in ampere turns and it will be represented by F. This will be related to another one which we are calling the magnetic flux. So magnetic flux will be measured in Weber, and the units are these Weber, BWB. Okay, so we are relating these four. Then those four are going to be governed by some equations, of course. So the governing equation between the magnetic flux density and the magnetic flux is this one. So B is basically flux over area. So we have that one as the governing equation for B and phi. And then we've got another governing equation in this where A is the surface area. So we've got another governing equation there. So the equation which is governing H and F is the length. So length is basically flux over H. So that is the governing equation there. Okay. Of course, L is the length. And we've got another governing equation. This one is governing B and H. So this one is basically that symbol phi, which is basically the permittivity. So permittivity times H will be B, and then we've got this phi and F, they are related by that one which we are calling the permeance there. Okay, but you need to note the following. This permeability is basically a product of relative permeability times the absolute permeability. So the relative permeability will be changing from time to time. It depends with the media you are in, but this one, the absolute permeability, is actually a constant. As I said, this is the permeability. So the absolute permeability is a figure which is a constant. So this is the relative permeability, which will be changing according to different media. And then this one is the absolute permeability. Absolute permeability is a constant, which is basically that 4 pi times 10 to the power negative 7. So this, they may give you or they may not give you, but you need to know that's a constant for the absolute permeability. Okay. We can look at an example, provided you know that box, the one I was presenting. It will be very easy to do problems in magnetism or magnetostatics. So the question here is saying a magnetic pole face has a rectangular section having 200 millimeters by 100 millimeters. Of course, that's the area. If the total surface or if the total flux emerging from the pole is 150 microweber, calculate the flux density. So they want the flux density. So from that box, what they want the flux density, and flux density said is a B. So we've got two equations relating B. We've got this one and that one. Which one to choose is according to what you've been given. So as we can see from our data there, they've given us the flux, which is 150 microweber. Flux is this one, and they've also given us the units or the dimensions which can help us to find the length. So if you multiply those, because they're saying it's rectangular, the area of a rectangle, it's length times base. When you multiply those, you're going to get that in SI units. It will give you this. Okay, so that is the area. So we have the flux and we've got the area. So finding the flux density will be very simple. So we are using that formula there. And then when you do that one there, which is saying flux density is the total flux, which is that, divided by the area of the core, which is A. Then when you substitute those figures into there, we're going to produce that 0.75 tera or Weber per meter squared. Those are the units for magnetic flux density. Okay, that was just an example. We can look at another one. Okay, we've got this one as well. a coil of tens, they've given us number of tens, 300 tens, is wound uniformly on a ring of non-magnetic material. The ring has a mean circumference of 40 centimeters, 40 centimeters, and a uniform cross-section area of 4 centimeters squared. So if the current in the coil is 5 amps, calculate. Number one, they want us to find the magnetic field strength, B, the magnetic flux density, and then the total magnetic flux in the ring. Okay, so with that said, in our solution there, we can analyze what we've been given there. So this is our data. We have the number of tens. They're saying it's 300. The length of that is 40 centimeters, which is basically 40 times 10 to the power negative 2 meters. They've also given us the area, 4 centimeters squared, or 4 square centimeters, which is basically 4 times 10 to the power negative 4 square meters. And they've given us the current as well, which is 5 amps. So with that said, of course, we're going to use this. So with that, the first one, they're saying we calculate the magnetic field strength. Magnetic field strength is the H. So the H comes from either this equation or that equation. So you check what you've been given. So from what we've been given, we know that magnetic strength, if we use this one there, it's basically force divided by length. So from this equation, which is here, we are making length the subject of magnetic field strength the subject of the formula. It's going to be force over length. So force, we know that it's the product of number of tens times current. That's why the units for force are tens, ampere turns. That's why they are ampere turns, because amps is coming from the current and then tens from the number of tens. So force is basically a product of number of tens times current, that divided by the length. So this one here, number of tens, we're saying it's 300. That's the one we have. The current is 5 divided by the length. The length there has been given to be this. When you do your math there, you're going to produce 3,750 amperes per meter. So that is the ampere turns per meter. So that is the value for the magnetic field strength. Then we go to B, which is saying for a non-magnetic material. So B is asking us to calculate the flux density, but we know for a material which is non-magnetic, it has a relative permeability of 1. Okay, thus the flux density will basically be supposed to be this one, but we know this mu is a product of absolute and the relative permeability, but the relative permeability is a 1. Therefore this will just be the absolute, which is a constant. So we know this value, a constant, 4 pi times 10 to the power negative 7, and H we've calculated, so you just need to substitute there. So 4 pi times 10 to the power negative 7 times the value for H. When you do your calculations there, you're going to produce 4.712 meters milliteract. So this is what you are having as your B, which is the flux density. And then we go to the last one, which is saying calculate the total magnetic flux in the ring. So the total magnetic flux now will come from this formula there. So the total magnetic flux, which is that phi, if you make it the subject, is basically the product of B and A. So B, we have it, we are just from calculating it, it's this one there, which is that one there. This mil is basically 10 to the power negative 3, that's the one you're seeing there. And then you're multiplying that by the area. So area is this one there, which is this one there. When you do your product there, you're going to produce 1.885 microweber as the total magnetic flux in that ring. Okay, I think this should help you to solve almost any question relating to magnetism. Thanks for watching.